right. Well, so let's see. The last class, everyone can see my screen, right? Last class, we started to calculate these entropy changes. And we did go through one. We worked on the isothermal, reversible, well, both irreversible and reversible. Oh, no, nothing coming out of the pen there. Huh, what's that all about? This always happens right after I hit record, right? It's gonna be one of those days. You're gonna do this to me. This computer completely died on me yesterday. Like, honestly, it took me, it wouldn't turn back on. I had to Google what was going on. And then, yes, close the program. Just close it. Man, I didn't even do anything and it whacked out. Anyway, it took hours for that thing to turn back on. All right, now at least it's working that time. Okay. Uh-oh. Oh, good. I thought it wasn't doing it again. All right. Moving right along. So last class, I started to calculate some entropy changes, and we looked at the isothermal expansion, which we've studied before. But we did it to calculate changes in entropy. All right, and we did this for the reversible and for the constant pressure cases, okay? And we were calculating delta S and delta S surroundings, and the general equation that we always use to calculate delta S is we start with the integral of dq reversible over T, okay? So even though we might be calculating a delta S for a process that isn't reversible, we still use that same formula because this is the definition of delta S. And for the surroundings, we use this. Okay, so this is dq surroundings. This is not necessarily reversible. This is for whatever the process is, whether reversible or not. Okay, so this is the actual. And this is always reversible, regardless of what path we're actually talking about. And we use these general equations, plus what we know about isothermal, reversible, and irreversible, AKA spontaneous, AKA constant pressure expansions to calculate these. So just sort of a little bit of review, because it's good to practice these things. So delta S, dq reversible over T. Okay, so, okay, what is dq reversible? Well, we know that for an isothermal expansion, we know that delta U is equal to 0. That means that dq is equal to the negative of dw. And when it's reversible, it's just the negative of dw reversible. And we know what dw reversible is. We know that it's minus p dv, where this p here is equal to P external. P gas is P external, and we just call it P. So this dq rev, like I said, it's minus dw rev over T, which is, okay, now dw rev has a negative sign. Minus dw rev does not have that negative sign. Wait. Yeah, it's wrong in my notes. I'm gonna fix that. Okay, but that is minus P dV over T. which is minus nRT over T dV. And these T's cancel. They would come out of the integral anyway, but anyway, they cancel, so we don't care. So this comes out to minus nR times the log of V2 over V1. And this is delta S for an isothermal expansion, and not just for a reversible expansion. This is delta S for any expansion, any isothermal expansion. So this is for the reversible or the constant pressure expansion, doesn't matter. And we could always write this as nR log P1 over P2 because T is constant. So P1 V1 is P2 V2, okay? So that's what we did for the delta S. For the delta S surroundings, well, for the reversible expansion, so now it matters what we actually did, what expansion we're actually talking about, because this is dq Ssurr for the actual process that we're talking about. And if it's reversible, this is, well, it's always minus dq. So dq Ssurr, this is another thing we used probably for the first time last time, that the dq Ssurr is the negative of dq. And since it's reversible, it's dq rev. So you could see where we're going with this. This thing right here and this thing right here, these are negatives of each other. And I'm not going to go through the whole thing again. I'm just going to show you that these are negatives. And so what that means is you're going to end up with the result minus nR log of P1 over P2. And that's delta S Ssurr for the reversible isothermal expansion. Okay, but what is delta S surroundings for the constant pressure expansion? All right, we start the same way. Again, this is minus dq over T. And now minus dq is dW. Okay, and that is minus, wait a minute, there's something wrong here. Yeah, I did something wrong. No. Huh. Wait a minute. It's easy to make a sign error when you're doing this, I'll tell you. Let's see. I think that this should not have a net. Something's, oh, okay. So delta, oh. Okay, yeah. I was looking at, this is delta S. Okay, good. All right. I thought I had a negative sign over here because I was looking at the delta S Ssurr one. And okay, but I'm fine. So this is minus P external dV over T. But now this is minus P2. Remember that P external is P2. So in other words, the final pressure of the gas is whatever the external pressure was. And we'd have to over T, right? And now, and that's constant, and T is constant also. So this boils down to minus P2, the integral of dV, or minus P2 over T, V2 minus V1. And this should look somewhat familiar because it's within a temperature, it's within a factor of T of what the work was when we did it for the constant pressure case. I'll show you. This is nRT over P2 minus nRT over P1. And then we factored, like there, we factored out the nRT, but now we're dividing by T, so we'll be able to cancel that. And this becomes 1, right? The P2 goes inside, minus P2 over P1. And did I forget a negative sign? Yeah, I did. So this is delta S surroundings for the constant pressure, isothermal, constant pressure expansion. Okay, so you have two different delta S Ssurrs that you have to use for the two different situations. This is for constant pressure, and this one over here is for reversible. But you use the same delta S expression. So it's delta S Ssurr that's different, not delta S. So all of that we did before. In the reversible case, you could see that delta S and delta S Ssurr add up to 0 because the expressions are the negatives of each other. And we did the example last time. We got 19.1 and negative 19.1. So when the gas expands and heat goes into the system and promotes that expansion, you end up with a higher entropy. Those particles are taking up more space. They're able to dissipate heat better. And with the reversible case, you end up with a delta S total of 0. Okay, which is part of the second law. So we're glad it verified that. For the constant pressure case that we worked on last time now, the delta S and the delta S surroundings, well, it uses this expression here instead of the negative of the delta S expression. This was still 19.1. This came out to negative something, 7.48. And that ended up being positive. So that delta S total was positive. All right. Now I looked up something over the weekend. How do I explain to students that why would the constant pressure expansion generate more entropy than the reversible expansion? And all right, the best I could do was I found a reference, and it makes sense to me. I guess you could say that whenever something is wasteful, it leads to a positive delta S total. And what's wasteful about this process? Why would you say that the constant pressure is wasteful? Well, the way I see it, you have a gas. Let's suppose the initial pressure of the gas is 10 atmospheres. It can push that hard. It can push for against 10 atmospheres. But at a constant pressure expansion, it might only be pushing against 1 atmosphere. It still ends up with the same change in volume, but it could have done a lot more work. And so so sometimes it appears that lost work implies a wasteful process, which are generally processes that generate entropy. In other words, a positive delta S total. And we're going to get to some other wasteful processes today that I think are even a little bit more obvious. So, I just spent the last 10 minutes going over what we did at the last bit of class last time. I hope that maybe that helped. Maybe it was just whoosh too fast, but it wasn't the first time I did it. So I wanted to go over it again. There's a weekend in between. You're working on a quiz that's on different stuff. So I wanted to go over it. I hope I didn't blow you out of the water. You guys okay? Okay. I see a few heads nodding. Maybe they're just falling asleep, but All right. Anyway, I don't think so. So what I'm going to talk about next is heating or cooling. Just a little more space here. And this is going to be heating or cooling to end up with a phase change that's sort of A, or B, which is heating or cooling resulting, that's really probably what I should have written here, resulting in a phase change or resulting in a change in temperature. So these are the two processes that we're going to talk about next. And you know, when we try to figure out delta S for various processes, we always have to do dq reversible over T. So I guess that leads to a burning question. And the burning question is, how do you heat reversibly? So what does it even mean to heat something reversibly? Because we have to do that if we're going to be able to calculate the delta S. So what do you think about that? We know how to do an expansion reversibly. We take off a grain of sand at a time. It leads to this incremental expansion. You know, you have a slightly lower, infinitesimally lower pressure outside than inside. Now let's take that to the heating realm, okay? So you want an infinitesimal amount of heat to transfer at a time. So what has to be true about the system and the surroundings for just a little bit of heat to transfer?
They have to be pretty much the same.
Same
temperature.
That's right. Okay, it means just like the impossibility, right, of having the same pressure inside and out. How do you heat something with the same temperature inside and out? Well, it's not quite the same, okay? It means you have to, so you need the surroundings to be just infinitesimally, hotter than the system. So that really the temperature of the system is equal to the temperature of the surroundings, except by an infinitesimal. Okay, so we couldn't do this. We couldn't heat anything reversibly without calculus. So here's a picture to illustrate this to you. Okay, adding heat resulting in a phase change. So for example, if I have a sample of liquid water here, all right, and I want to vaporize that water, right, because I'm talking about a phase change. So I want to vaporize it. Well, I know that the boiling point of water is 373.15. And if I put heat into the system at that temperature, I know that temperature won't change until all the heat has been converted to gas. And I have to have a bath that has basically the same temperature, but just a little bit more. So if this is 373.15, let's make the bath 373.20. So I'm considering that 0.05 degrees C is infinitesimal. It's not, of course. But I could have said 0.000001 degrees C, but you know, for the purposes of this argument, I don't really have to say all those zeros. I think you know what I mean. So what'll happen is I keep my bath at 373.20, or infinitesimally higher than the water. And this is a very big bath that I've drawn here, you know, or I could even have a heater that's heating my bath up and keeping it, thermostating it and keeping it at 373.2. And then I'm going to get an infinitesimal transfer of heat. Okay. The heat will have been transferred reversibly. So I'm talking about an infinitesimal at a time. And it's really dq rev because it's done reversibly. So throughout the entire process, we can say that the temperature of the system, which we just call T, is about equal to the temperature of the surroundings. And that's what we mean by equilibrium when we're talking about heating, right? So it's not like mechanical equilibrium anymore. It's really temperature equilibrium. Now, why would I call this reversible? So what does it mean to be reversible? It means that you can reverse it by changing something by an infinitesimal. So basically, instead of having the temperature of the bath infinitesimally higher than the temperature of the liquid, I could go the other way, and I could change the temperature. By the way, I probably should put a cover on this or something with that gas. It's just going to escape. But so I can have the bath be infinitesimally cooler, and that would cause the heat to go the other way. So this is reversible because I can have the bath. So I could change the temperature of the bath, I guess I should say. Just a little. And the heat will go from the system to the surroundings instead. In other words, the process reverses. Okay, that's what I mean by reversible. All right, so that's nice. How would we do this for the second thing we're going to look at here? I said we're going to look at two things. What about adding heat to result in a temperature change? Okay, so what about resulting in a temperature change? So I have this other nice picture for you. Okay, and so this is a little harder, right? Because now you have your system. Let's suppose you want to heat a sample from 300 to 310 Kelvin. So you'd start out, you'd have your bath at 300, your sample at 300, your bath at 300.1. And you would transfer an infinitesimal amount of heat, little teeny tiny arrow that way, okay? And now that your water is at 300.1, you'd have to change the bath temperature, go up a little bit more, have another little infinitesimal, keep doing that, okay? You could see that this could be very time consuming, okay? But what happens when you do it this way, yeah, this could take a while, is that T equals T surroundings at every step in the process, so that the heat was transferred reversibly. Okay. And you could reverse it very easily, right? Instead of increasing the temperature, you would decrease the temperature, and then the heat would have to go the other way. So this is also reversible. Okay, if you cool the surroundings, meaning the bath, a tiny bit, then a tiny amount of heat flows from the system to the surroundings. I said that right? Yeah, okay. So that's reversible heating. So what's irreversible heating? So what's sort of the opposite of this?
Would that be like combustion?
Now let's think about, let's put our minds on this picture right here. You know, what would be different about this picture? Okay, what would be different about that picture? But yeah, you're right, combustion is not going to be reversible, but let's talk about heating and cooling something, because that's what we're in right now. So what would have to change about that diagram in order for it to be spontaneous or irreversible?
T would not be equal to T surrounding.
That's right. You would have to have, if you were going to heat the system, the temperature of the surroundings would have to be considerably higher, or somewhat higher. Or T Ssurr would have to be less than T for cooling. And of course, when I don't put a subscript, I'm talking about the system. So it has to be not just infinitesimally hotter, but really hotter, okay? And then this would be a spontaneous, really a directed change, right? If you had your system here at, I don't know, 100 degrees C, and you have a bath here at, 400, I better not use degrees C. How about if I just say, I don't know, 100 Kelvin, doesn't matter, it's not talking about water, 400 Kelvin, boom, that heat is going that way. And if you change it if you cool it to 399, it's still going that way, right? This is a directed change. This is spontaneous. Okay, there's a big delta T. T and T Ssurr are not the same. This is not equilibrium. Okay. All right. Well, this leads me to a really big question, a really important question. So here's the big question. And that is, does the amount of heat transferred to the system reversibly differ from the amount of heat that would be transferred spontaneously or irreversibly? So, what do I mean here? So, okay, so we have a process. Let's say we have a process like a phase change, and we very carefully transfer the amount of heat, a little at a time, to that liquid water to get it to vaporize. So I suppose we're talking about that process. So suppose we use an example. The vaporization of 1 mole of water to the gas state at, the boiling point, 373 Kelvin, with the reversible addition of heat. Okay, so I'm going to use this example, vaporization of water. Okay, and we're going to contrast that to the same process, but where the heat was transferred irreversibly. So we're still taking 1 mole of water. We're going from 373 Kelvin. We're at 373 Kelvin, and we're going from liquid to gas. And let's say the bath here is at 500 Kelvin. So here we have a 1 mole of water, liquid to gas, with a bath at 373.1 Kelvin. So we're looking at these two different processes. My question is the amount of heat required to do that phase change any different? Is the amount of heat in each case to convert all the liquid to gas, any different? What is that amount of heat? What is the amount of heat required to convert a mole of H2O from liquid to gas at the boiling point? We know what that is, right? We have a name for it. What's it called? Right? It's called the heat of vaporization, right? So you need, this is 40.67 kilojoules per mole. So 40.6, this is delta. So they both require that same amount of heat. If you put 40.67 kilojoules of heat using a 500 Kelvin bath versus 40.67 kilojoules of heat using a 373.1 Kelvin bath, what's the difference in those two processes? Well, one is going to be a lot faster than the other, because when the temperature difference is greater, the heat will transfer more quickly. But that same amount of heat will be required to actually effect that change, all right, to change that water from liquid to gas. Okay, so it would be is the amount of heat in each case any different? And the answer is emphatically no. The amount of heat is the same. And you can ask yourself a parallel question, right, about the other process. Like, suppose we're taking liquid water at 300 and we're heating it to liquid water at 320. Okay, so that's like from 27 degrees C to 20 degrees higher. Okay, so, and let's suppose you do this reversibly versus irreversibly. And this is reversibly, where you have a bath temperature that's at first, it's like 300.1, then 300.2, the 300.3, etc. Or maybe you use a bath temperature that's at, at 400 Kelvin. And you don't bother changing what the temperature of the bath is, you use that the whole time. So my question is the amount of heat transferred from the surroundings to the system the same in these two cases, the reversible versus the irreversible? So what is that amount of heat? What is the heat required to do that? These are all things we've learned already, okay? We know that the heat, which if we do this, let's say at constant pressure, okay, that's the easiest way to do it, 1 atmosphere. Okay, then Q is QP. And as long as no extra work is done, that's their delta H, which is a state function enthalpy. So it doesn't matter how you do it. Okay, but what is it? It's NCP. Well, it's actually NCP dt integrated. But, I'm going to go with the easy thing, that CP is constant in the small temperature range. So it's going to be NCP times delta T. This is the constant pressure heat capacity and the number of moles. Delta T is going to be 20 in both cases. This is the same. CP, heat capacity of the material, is not going to change because you heated reversibly or irreversibly. Okay, so basically the heat is the same. Whether it transfers reversibly or irreversibly. Okay. So here's another little fact that we have to use from time to time. And that's why this gets kind of complicated, right? So dQ reversible equals dQ for heating and cooling, resulting in a change in temperature or a phase change. Could I say that about the isothermal expansion? No, I could not, right? Because in the one case, we had dQ equals dQ rev, which is dW rev, which is minus P gas dV. And then we have to keep the P inside the integral, right? But in the other case, we have dq is minus dw constant pressure, right? So then we use the minus P external dV, and the P external comes out of the integral. So you can't use this all the time. That's why I'm saying here, you can use it for heating and cooling, resulting in a change in temperature or a phase change. All right. Yeah, I know, that's wonderful, right? Another thing to remember. But, you know, write this down on your special pad of things that you should know, okay? I don't have one of those either, but. Okay, so you could see that this unit is a little complicated. All right, and what that means is that you should really go over your notes after class. You should see if you really get them, okay? Because if it gets too far and you haven't done that, you'll be overloaded. So that's my recommendation. It's complicated, you should pay attention. You should ask lots of questions and, you know, and give it some time, because this is not that easy. So what I'm going to do next is calculate delta S and delta S surroundings for these processes that I've been talking about. So heating resulting in a phase change, heating resulting in a change in temperature. And these are sort of formulas that we use to figure out lots of different things. So anyway, so 1A, I can put a 1, just call it A. A was phase change. And what I'm going to do is do it at constant pressure, but then I'm going to show you, well, phase change is at constant pressure, yeah. So delta S, what's delta S? Integral of dq reversible over T. First thing I get to do is I get to say, oh, that's just dq over T. Doesn't care, okay? It's the same amount. And since it's constant pressure, it's dqp over T. Now, what's dqp?
Is that dW?
Yeah, it's dH. Delta H is QP, dH is dQP. So we proved that a long time ago. And one of the things we needed to prove that was that there's no extra work, there's no non-PV work. So we're using that. Okay. So it's dH over T. Okay. And now a phase change occurs at a constant temperature. So we get to take this out of the integral. So we end up with 1 over T times the integral of dH. And I love the integral of dH because H is a state function. The integral of dH is H2 minus H1, which we call delta H. So this is the delta S for a phase change. We normally use the per mole, and we give it the subscript phase. So this is per mole. This is the standard standard change in enthalpy for a phase change. And it's delta H 0 over T. Okay, so let's figure it out. Oh, by the way, this T is the temperature of the phase change. I'll just put phase there. So this is like for water, this would be the boiling point, okay? So this is 40 in joules, it's 40.67 kilojoules per mole. So it's 46.7, because usually for entropy, we do joules instead of kilojoules. divided by 373, and we get 109 joules per Kelvin per mole. Okay. So that's the delta S0 for H2O. All right. So, of course, if you had 2 moles of water, you'd have to multiply this by the number of moles. So don't forget a thing like that. Delta S0 phase, you have to multiply it by the number of moles, okay, to get the delta S for the particular process. All right, so now I'm going to tell you there's actually a rule. It's called Troughton's rule. It's on a lot of GRE exams and things like that. They throw this thing in out of the clear blue sky. And the Troughton's rule says that if you take the delta H of vaporization for 1 mole and you divide it by the boiling point for a series of liquids, that generally they all give you 85 kilojoules per mole. Well, water is always an exception because of its massive hydrogen bonding. But I'm going to show you a chart. I wonder if it's coming up. We'll see. Oh, look at that. I did a good job there that time. So here's a series of compounds. You have very different things in here. I mean, you've got H2S, you've got benzene. And you could see that 85, okay, 87, that's not bad, 84, 86, 87. The ones that don't work too well are the hydrogen bonding liquids. But why do you think this is? So delta S0 is delta H0 over T. So what affects the boiling point? What affects the heat of vaporization? So why does, so here we go. Here we have H2S, we have benzene, we have all these different things in here. Notice water's value is much higher than the others. Okay, so what affects the delta H of vaporization? It's affected by intermolecular forces. What affects the boiling point? It's also affected by intermolecular forces. In the same way, if you have a lot of intermolecular forces, it's gonna mean you need more energy to separate molecules. It's going to mean that you're going to need a higher temperature for enough molecules to break away to the gas phase that you have boiling, which is when the vapor pressure in the gas phase equals the atmospheric pressure. So that's what the TVP is the temperature when P vapor pressure equals atmospheric pressure. Okay, so both of these things, these both increase with increased intermolecular forces. So, if they depended on intermolecular forces in precisely the same way, right, then this number would just be constant for every single compound. But hydrogen bonding apparently increases the delta H more than it increases the boiling point. I'm going to say apparently. Increases delta H0 more than it increases the boiling point. Okay, so that's why you have these anomalously high values for water and for ammonia. Okay, more hydrogen bonding, the higher that number is. So anyway, there's an interesting little fact. I hope you enjoyed that. All right. All right, okay, so what am I going to talk about next? All right, so we now have delta S for a phase change. What do we still need? Is we need delta S surroundings for the phase change. We haven't gotten that yet. okay? And delta S surrounding. So this is the formula I gave you before. This is the equation, dq Ssurr over T. But now I have to tell you that I lied a little bit, that this is not really the right equation for delta S Ssurr. It's just another one of those cases where I don't want to put all these crazy things in all at once. And so I didn't tell you that what the real formula is dq Ssurr over T Ssurr. That really I should be using the temperature of the surroundings. So this is kind of wrong. So I lied a little. But I prefer thinking about it as oversimplifying, because I didn't want to just throw everything at you all at once. But now that we're actually going to use this to calculate something where it matters, well, it mattered before, but we didn't. Anyway, so we're going to use this correct formula. Okay. So let's see. So now I have to do two separate calculations. I have to do this for the reversible situation, for when it's reversible heating, and for when it's irreversible heating. See, I didn't have to do that for delta S, because delta S is defined for the reversible process, but I have to do that for delta S Ssurr. So here we go. If it's reversible, right, then this dq, so first of all, before I even use reversible, what do I know always about dq surroundings? It's always negative dq. Whatever heat went into the surroundings came from the system, and vice versa. So this is minus dq over T Ssurr. Oh gosh, I'm doing the reversible, not the, sorry, I want to do the reversible one first. So we'll do the irreversible later. So make sure, you know, this is for the reversible. I'll give you a minute to change that, sorry. Okay, so minus dq, but since it's reversible, this is minus dq reversible over T surroundings. And also, since it's reversible, T surroundings is equal to T, right? Because it's reversible. So this becomes minus dq reversible over T, okay? Oh, and I honestly didn't even need to put this reversible in here because dq reversible equals dq for heating, resulting in a phase change. So I didn't even really need to do that. Could have skipped those. I'm back here again because I lost my sign, okay? All right, so let's look at this. dq Ssurr over temperature of the surroundings. dq Ssurr is minus dq, which is the same as minus dq ref. So we're just going to write it as minus dq. At the same time, T and T surroundings are the same. So I end up with minus dq over T. And now, since I hope I said that I want to do this at constant pressure first, I'll show you how it changes for constant volume. But constant pressure, this is dqp over T. This is a phase change, right? So in a phase change, T is constant. So this is minus dQp with the 1 over T on the outside, which is minus 1 over T dH. So this is because it's constant pressure. Yeah, I'm not liking how messy I made that, so I really would like to do that one again. So I'm just going to repeat this and try to make it a little more simple. Delta S surroundings is dQ Ssurr over T Ssurr. But dQ Ssurr is always minus dQ. Okay, we're talking about the reversible situation. So T surroundings is T. We're talking about constant pressure. So dQ is dQp. And it doesn't matter if it's reversible. So this is dQ rev is equal to dQ. So we're just going to leave it as dQ. But we're going to put the constant pressure there. And that's how it gets to be minus dH over T, but T is constant because of the phase change. So this is minus 1 over T dH, but the integral of dH is delta H. So we have that delta S surroundings for the reversible phase change is negative delta H over T. So delta S surroundings for 1 mole is negative delta H 0 over T. Hope that was a little simpler. All right. And lo and behold, this is the negative of the delta S. Okay, so delta S plus delta S surroundings is going to be equal to 0, which makes sense because it's reversible. All right, so this, for 1 mole, this would be negative 4670 joules over 373 Kelvin. It would be negative 109 joules per Kelvin, which is, like I said, it's the negative of the delta S. Okay, so you'd have 109 minus 109 for delta S total. That's okay. That's what we want for the reversible case. So let me just go back. And how did we start this? Because we're going to start it exactly the same way for the irreversible case. We start with this definition here. Okay. So again, this is now for the irreversible case. Delta S is Ssurr is the integral of dQ surroundings over the temperature of the surroundings. Okay, so this is minus dQ over T surroundings. And this is minus dQp, because we're going to stick with constant pressure for now. So this is negative dH over T surroundings. But now, this T surroundings is not the same as the temperature of the system. So we took it out of the integral before, but now it's just a different number. So delta S surroundings for the irreversible phase change is minus delta H for the phase transition over the temperature of the surroundings. So that's not the negative of delta H for the phase transition over T of the boiling point. Okay. So we have, this is our delta S surrounding. So if it's for 1 mole, we would put a little 0 there. And we had delta S for 1 mole was negative delta, was just plain old delta H phase over the temperature. That's the boiling point. And these are not the negatives of each other. You'd have to multiply both of them by the number of moles if you have more than 1 mole. So basically, delta S surroundings depends on the bath temperature. All right, and this is where we get up to figuring out, you know, what the total entropy change is and how, if you have a hotter bath than you need, you actually have wasteful heating and you have a greater delta S total. So let me show you how that works. So, so I'm going to calculate delta S and delta S surroundings for 1 mole of liquid water undergoing a phase change to gas. With the bath temperature at 500 and at 600 Kelvin. And we know that, of course, the actual anyway, so for the 500 Kelvin bath, delta S surroundings is negative of delta H0 over 500 Kelvin. That's T surroundings. Let me just put the numbers, 4670 joules. So this is negative 81.3 for 1 mole. But if you did this at 600 Kelvin, you get a different number. And remember, delta S for this process was positive 109. So if you add these up, with the bath temperature at 500 versus 600, you get 109 minus 81.3, or 109 minus 67.8. So this is delta S total. Okay, and don't forget that when we had the reversible case, we had just 109 minus 109. Sorry, this should say delta S surroundings here. Okay, so the higher the temperature, the greater the positive entropy production. And so that's kind of what we generally see, is the more wasteful the heating, the greater the positive entropy change, total entropy change. We call it entropy production. The more entropy is produced, because we have this wasteful, he was sort of wasted that nice hot temperature bath on something that it didn't need to be that hot for. Okay, how are you folks doing? Kind of, all right. Yeah. Yeah. So that is heating resulting in a phase change. But I did promise you another process today. And that was heating or cooling resulting in a temperature change. First, yeah.
I just want to be sure. So the reason why it's wasteful is because you don't need all that much heat.
Yeah.
Okay.
So you used a bath that had a lot of heat energy, and you could have done something that really needed that heat, but instead you did something that didn't need it all.
Okay, I just wanted to make sure I had that.
Yeah, that's right.
Thank you.
Sure. All right. All right, so now, okay, so what if I do this heating at constant pressure? Okay. So remember, it doesn't matter if I do this reversibly or not, but it is reversible in this case. So I'm just going to call this dq, which is dqp, and dqp is dH. Okay, so what is dH for heating or cooling? You have a substance, you heat it up. How much heat will it absorb? What does it depend on? Well, it depends on two things. It depends on what the change in temperature is and what the heat capacity is of that material. So this dH is NCP dt. That's a familiar formula, right? We've used it before. I even gave it to you earlier today. But I don't remember why. Okay, so this is what we have to figure out. And you know how sometimes I tell you that CP depends on temperature and you have to integrate all the terms? Well, when we do entropy problems, we never do that because, you know, how complicated can I make it? I mean, I don't want to make it infinitely complicated, right? So we're just going to say that we're going to assume that CP is constant over the temperature range from T1 to T2. This is dt, we're integrating dt. So we have NCP, the integral of dt over t. Remember I told you that's the one integral you have to know is dx over x, and that's natural log. So it's NCP log of t, T1 to T2. So it's this delta S is NCP log T2 over T1. So this is for heating at constant pressure resulting in a temperature change. And this could be reversible or irreversible. Doesn't matter. It's going to have the same formula for the delta S because we always use the reversible. Okay. I wonder if I have to, I probably should write this here. It doesn't matter if we heat reversibly or not. Okay, now what if we did this at constant volume? Suppose we did this at constant volume. So what would be different? So we would start the same way, except instead of saying constant pressure, right, we'd say constant volume. So this would end up being, instead of dQp over T, it'd be dQv over T. What is dQv? So if it were constant volume, this would be dQv over T. That's du instead of dH. And this would be NCV dt over T. And that's, you would get NCV log of T2 over T1. And this would be constant volume, reversible or irreversible heating, resulting in a change in temperature. Okay. All right, so that's the delta S. But for delta S surroundings, we have to do different calculations for reversible and irreversible. Okay. So delta S surroundings. Okay, again, dq Ssurr is always minus dq. It's constant pressure. First, I'm doing constant pressure. So this is dqp over T Ssurr. Again, this is a negative dH over T Ssurr. But now here's the difference. The bath temperature can come out of the integral because it is constant. It's not reversible. Hold on. Oh, wait. Sorry. I didn't tell you if I was doing reversible or irreversible. So now that's where I have to, oh, wait. Right. I could stop right here. So this is true for reversible or for irreversible. I haven't said, I don't say anything about the bath temperature. So far I have this. That's true for both. Okay. And I can put in NCP dt over T surrounding. So the difference is, of course, I have this negative sign I didn't have before, right? But I also, instead of having T here, I have T surroundings here, which if it's not reversible, that's constant. If it is reversible, that's the same as the temperature of the system. So I'm going to use this as a starting point. So now I have two different things to do. If it's reversible, right? Or if it's constant pressure, if it's irreversible, which means T Ssurr, we could call it constant. And reversible T Ssurr equals T. Those are the two big differences here. So if T Ssurr is equal to T, then my delta S surroundings is going to be minus n Cp. Let's assume that these are constant over the temperature range. The integral of dt over T. I'm changing T Ssurr to T. However, if it's irreversible, I'll still take out the NCP, but now it's dt over T surroundings, but this can come out as well. So I'll have delta S surroundings is N minus N Cp over T surroundings times T2 minus T1, because that's what the integral is between T1 and T2. This is for spontaneous or irreversible heating. And this is for constant pressure. This thing would be the negative of what we got for the delta S, would be minus NCP log T2 over T1. So this is for reversible heating at constant pressure. What about if I did this at constant volume? Well, the only thing that's going to be different is that this is going to be CV. Because if you remember, we just had, we would have du instead of dH. All dH's become du, and that's NCV dt. So at constant volume, this would be minus NCV log of T2 over T1. And this one would be minus NCV T2 minus T1 over the temperature of the surroundings. Okay. I'm going to show you, I posted a sheet of equations. Now, I know that you guys won't be taking any in-class exams, but it's still a good idea to have a list of equations, okay? And I always tell my classes that they should, in PChem, they should familiarize themselves with this handout. And this handout has a lot of useful things on it, but it also lacks a few things that students might also find useful. I'll show you what I mean. So I have a lot of nice equations here. You know, I've got the equations for the adiabatic expansion, constant pressure. This is the constant pressure one. This is the reversible one. You use these for that special problem that I'm grading now. It's got the first law, it's got the second law, it's got some other useful stuff. But it has a lot of entropy equations on it. And I didn't put the whole thing. I just stopped because we're up to this at this point. So here is your definition of ds and ds surroundings. And of course, to calculate the deltas, you integrate these things. And that's down here and down here. I have the phase transitions here. I don't put the zero, but if I put the zero, if I don't, it just means you have to multiply by the number of moles. All right, so then I have all these equations here, all right? So here, and this is the way I give it to students for a test. If you were taking it in class, you would have to know which of these corresponds to which situation. Because look at all these equations for delta S and delta S Ssurr. Right, so the thing is, if I were you, I would go through these quickly and write down what they're for. Okay, I'll tell you. What is this first one for? NCP log of
pressure.
So this is constant pressure. Oh, my pen is too fat here. Oh, I know. No. Oh, here. So we know it's constant pressure. But what's the process there? We know it's heating or cooling to get a delta T. Notice because there's a T2 and a T1, so there has to be a change in temperature. And this is the delta S. So this is for reversible or spontaneous. It's the same equation. But let me just make sure we got the right answer here. Yeah, see that? This equation here is for spontaneous heating. And that's what we got here. This is for spontaneous heating, constant pressure, okay, bath temperature is T Ssurr. This, how is this, what's different about this equation here? So this is the negative of this. So this is for reversible heating. So that's delta S Ssurr for the reversible case. So, and here is the same equations, but for constant volume. And you could see that because we have a V here. And this is a set of equations for the isothermal expansion that we derived last class. You could see that this is for the reversible and the spontaneous case. So, you know, there's advantages of having this class be online in terms of, you know, what you have to memorize and what you don't have to memorize. There's a lot less deriving in this class because I asked students to do that. They can just copy it out of their notes in this class. So, you know, maybe that's why that, I mean, I think this quiz I wrote is the easiest one so far. I hope that you agree. The one I just gave out. I took out some stuff before I gave it out. I said, oh, forget it. I'm not going to do that. But yeah, I think that the quizzes have been harder than the ones in the class because you're not in class. So you get all these things right in front of you. You take infinite time to do the test. So anyway, that's kind of, I don't know. So like if you started to do the test or the quiz and hadn't done any of the work, you could still do it, but you'd have to learn that stuff while you were doing the quiz. And I think a lot of people do that in Gen Chem as well and on the online version. So I hope that every quiz has been a learning experience. That's kind of, I think that it's different when you do it online. And I think there's more of that. I don't know, what do you think about that? I don't know. That's kind of the way I thought about it. Anyway, I'm not going to do any more today because that was enough. Next time we're going to move on. We're going to just do an example. And then we're going to do, we're going to look at, oh, by the way, yeah, I probably should tell you this just to show you where we're at so far. So this was assignment 4 that I gave out. I think I posted it recently, maybe last week, but I know it's up there now. And so I have all these 1, 2, 3, 4. So I wanted to say that, you know, we've done 1, we've done 2. These are about the isothermal expansion, reversible, constant pressure. And then we didn't do 3 or 4 yet, but we did 5. That's what we did today, and 6. So this is about heating. And the next thing we're going to be working on is 3 and 4. And these are adiabatic expansions. So we're returning to that on Wednesday. And I'll talk about how to calculate the entropy changes for when those expansions are done reversibly and not reversibly and irreversibly. Anyway, So yeah, and this unit, this part of the unit is the most complicated part of the entire course. It's just that way it is, that it's just that way. So, okay, I'll see you at 6. I'm going to talk about charge transfer a little bit tonight. That's the lab I'm interested in. Anybody know what the next lab? I don't know. What was next after that? The online people. What did you do after charge transfer? Was it naphthol? 2-naphthol? I don't know. I have to look it up because whatever was on that schedule, that's what I'm going to do. Talk about next week. Okay. If everybody who hands it their charge transfer calculations, I should have gotten them back to you. Did you get them back? Because my computer died in the middle of all that, but I think I mailed them out. So, but some of you didn't hand them in. So if you don't hand them in, I can't comment on them. All right. Well, I'll see you later at 6, the same time, same station. All right. Go get some rest before 6 o'clock. Mm-hmm.